As part of this closing keynote, I have Shanna Knights from Ballard Power Systems with me. Shanna is Director of Technology Collaborations at Ballard Power Systems, and her fuel cell research areas have included durability, reliability, performance, and operational behavior of fuel cells. She's also responsible for both internal research activities and significant collab with universities, research institutions, and industry. Her work has focused on improving fuel cell cost, durability, and functionality. She guides Canadian and international academic, government, and industrial fuel cell research through service on advisory boards and steering committees. With that, I'd like to extend a warm welcome again, Shanna. Welcome to the keynote.
Thanks, MBI.
And with that, I'll leave the floor on to you to guide us through life cycle emissions and the sustainability of Ballard products. The floor is all yours, Shanna. Thank you.
Great, thank you. Okay, good afternoon, everyone. Thank you for tuning in for the last talk of the day. I'd like to thank the organizers for inviting me to give a talk today. And I'm going to be talking about zero emission buses and sustainability over their life cycle. So as we all know, why we're here today is that we need to reduce greenhouse gas emissions, and particularly we're talking about transit buses today, and we know that electric buses are going to help us do that. For electric buses, I'm talking about both fuel cell buses and battery electric buses. We know they're both needed. So, Ballard makes fuel cell buses, and we make fuel cells for fuel cell buses, as well as other heavy duty applications. I think you've heard a bit about that. But we've been working with making fuel cell bus power systems for a couple decades, and it's something that's needed going forward. And we need fuel cell buses work with batteries, so they're complementary. So it's not about either or, it's about both. And we've heard some about that, about the different route choices. Some will lend themselves well to battery buses, and some will lend themselves well to fuel cell electric buses. What I want to talk about today is looking at, we know in operation that both fuel cell electric and battery electric buses have zero emissions at the tailpipe, as it were. But what we also need to consider in the longer term is what's the complete life cycle of the bus, and what's the environmental impact of that life cycle. So what is the impact on the environment of producing those batteries and those fuel cells? And also what happens at the end of life? So we have to look at it as a whole lifetime for the power systems. The buses are only as clean as their fuel. So what's happening, we know what's coming out of the bus, but what about what's going into it, and how is that produced, the hydrogen or the electricity? Sorry, next slide. Sorry, I'm behind on the slides. Go another one. Okay, so the buses are only as clean as their fuel in operation. It's great for point of use, producing zero emissions, but there's also the fuel that goes into it. So next slide. So not all fuel sources are equal in terms of the greenhouse gas emissions. So looking at electricity sources to start with. So this is a map of the greenhouse gas intensity of electricity generation by province and territory in Canada. And we see that there's quite a difference. So some provinces are quite fortunate to have a lot of hydroelectric, companies like BC and Quebec and Manitoba, but other provinces aren't as fortunate in that capability, and so they have to use more polluting sources to produce their electricity. So if you're running a battery electric bus, are you running it off of a clean electricity grid or a polluting electricity grid? So that's something to be looking at and concerned about. Next slide. So similarly, when you produce your hydrogen that's going to be used for your fuel cell electric bus, it can come from different sources, and that we have we call different colors of hydrogen to indicate how clean they are in terms of greenhouse gas emissions. So we have gray, blue, or green. The gray hydrogen is what's normally used today, most predominantly, but of course we're trying to change that. And that's based on natural gas that's been reformed to hydrogen. And when that happens, there's some CO and CO2 that gets produced and has a greenhouse gas impact. It's still a good approach. You still have lower emissions than you would if you're running a diesel engine because you have a more efficient process. But much better is going to blue hydrogen. So that's an interim approach where we have the natural gas is reformed to hydrogen and the carbon and carbon dioxide is captured by carbon capture sequestration. And so that's when the carbon is captured and is usually then injected into the ground or into geological formations in the ground where it's going to stay there for thousands of years. So that has a very low greenhouse gas impact. Or we have green hydrogen, which is of course the ideal. And that's where you use renewable electricity, such as from hydropower, wind or solar, and then you use electrolysis to split the water into hydrogen and oxygen. So that's the ideal longer term scenario, and there's a lot of work going on around the world, a lot of work ramping up on electrolysis to make it cheaper. And so we see within a decade that we should have very cheap green hydrogen coming online. Next slide. So this just shows in another case study, basically the use of green hydrogen and how it enables drastic reduction of greenhouse gas emissions compared to diesel buses. So this case study is fuel cell buses powered by green hydrogen produced at scale, so in larger volume, at a central location from renewable energy, and then it's transported via pipeline over a long distance. And they take into account, in this case, the hydrogen is produced using solar energy. And so they take into account that production as well as the transport. And what we see is that you can get a 90 to 95% reduction in greenhouse gas emissions for the hydrogen fuel cell vehicle case compared to an equivalent diesel internal combustion case. From 2030 to 2050, the impacts go down further, and that's based on some expected improvements in the compressor to move the hydrogen through the pipeline and some auxiliary energy supply for operating the hydrogen refueling station. Next slide. So that's a great case with green hydrogen, but we also see a pretty big impact with blue hydrogen as well. So in this case, we're looking at the life cycle emissions intensity for a 40-foot transit bus operating in Alberta. And it's done the analysis using various sources and drivetrains. And what we see, if we look, we see the diesel bus and the life cycle emissions. We see a lot of the emissions are at the tailpipe. That's what we all know. If we use a compressed natural gas engine and fuel, we see that we reduce those tailpipe emissions by a bit, but we also have some impact from the refueling or from the fueling. So we see some reduction, which is great. But if we then go to a battery electric bus, we see that the emissions are dropped by 50%. And most of the emissions there are based on the power generation. So basically, how do you produce that electricity? If we look at the fuel cell electric buses, the first one using gray hydrogen, which again is just reformed methane to reduce the hydrogen, no carbon capture. Then we have not quite as clean of an impact as we have with the battery, but still about 40% reduction compared to the diesel. And most of the emissions there are based on the hydrogen production that we've just talked about. If we then have blue hydrogen, so still using natural gas to produce the hydrogen, but now you're capturing that carbon, then we have 83%. So that's a best case, 83% emissions compared to the diesel. So this is in a case where you have your grid is not as clean. And so that's where a fuel cell electric bus can really have the biggest impact. Longer term, we hope that the grids can be cleaned up and that we'll have both battery electric buses and fuel cell buses would have the significant impact that we all know that we need, and both will have drastic reduction. Next slide. So just looking a little bit more at the complete life cycle. So we want to look at not only the operational phase of the bus that I've just been talking about, but what's the emissions that are generated during the production of the vehicle, including the fuel cell engine and batteries, and the end of life. What happens to it after it's operated? So we call different scopes of emissions. So we have, in producing your fuel cells or your battery, you have your scope 3, which is kind of a result of indirect and the greenhouse gas emissions that result from firms' operations when they're producing those. We have the operational emissions, which includes those emissions for transmission from the grid, for producing your hydrogen, for producing your electricity, and no scope 1 emissions from actually operating your vehicle. And end of life, again, it's scope 3, and here again it's indirect, but it's what happens to the vehicle, what happens to the engine after it's been operating and it's no longer produce enough power. Do you just have to throw those into the waste, or can they be recycled or reclaimed? So next slide. So of course, Ballard makes fuel cell power units. So we've gone into a lot of detail, and this is something that's going to be something that we're going to be focusing on a lot, is making sure that we know what the environmental impact is of our fuel cell engine and how do we influence that and reduce it. So next slide. So this is a fuel cell engine, just a schematic and an actual picture. So the fuel cell engine consists of the fuel cell in a number of unit cells, each one producing power, and those are stacked, and we call that the fuel cell stack. And then those are combined with things like air handling, like air compressors, fuel handling, water management and thermal management, and controllers. And that's the balance of plant, and that's the whole fuel cell module. Now, most of the components within a fuel cell stack are either graphite materials, so carbons, or metals, and basic metals like aluminum, steel, and precious metal in the form of platinum. So there's very little range of more exotic metals and materials that can happen in batteries, for example. So it's relatively simple in terms of the materials produced. Next slide. So what we've been working on over the past couple of years is really making sure we understand what our greenhouse gas footprint is of our products. So we've done life cycle analysis from cradle to gate. So from basically the production of our products until we ship it out. So that includes, doing that analysis includes looking at the extraction and processing of raw materials, the manufacturing and assembly of the components, upstream transport, and manufacturing and assembly of the power module at Ballard's facilities. And so we've compared our previous generation, or the one that's doing most of the operation right now, which is the FC Velocity HD85. And the greenhouse gas emissions for that are about 6,400 kilograms CO2. If we then compare to our FC Move, which is our latest and newest module, then the greenhouse gas emissions have been reduced by quite a bit to the 5,000 kilograms of CO2. And what we can see is that we've reduced it in the plot. You can see the gray bars is the MEA, and that's been reduced a little bit. And the brighter blue, the most of it, is the balance of plant. And that's where we've reduced it significantly. And we've reduced it overall through less components, making it simpler, which also helps us to reduce cost, and less platinum. So this, on a kilowatt basis, we've reduced our greenhouse gas emissions by about 6% compared to the new design. And that's something going forward, it'll be a design input for us. What are the greenhouse gas emissions of any design decisions we make? How do we make sure that we're minimizing those as much as possible? Next slide. So this looks into a little bit more detail of the same analysis and what is actually contributing to those greenhouse gas impacts. And the highest greenhouse gas impacts for the production of our stacks was the production of metals for the membrane electrode assembly and in the balance of plant components. So if we look at the MEA, the first bar on the left, that's the membrane electrode assembly where the power is produced in the fuel cell. And the biggest component representing the greenhouse gas carbon footprint is the platinum. So platinum is a mined material, and the mining of it currently has a significant greenhouse gas impact, but mines are starting to look at how can they reduce their impact, and they're doing things like implementing the use of fuel cells or battery vehicles and looking at how they can reduce their greenhouse gas impact. Additionally, this analysis assumes no recycled platinum. Now we do recycle our platinum, and eventually, we have to look at including that in our analysis, but for the first run around, we didn't include that. So that will reduce the platinum impact as well. So when we make decisions for where we're going to source our platinum, we can start to look at what is the greenhouse gas impact, and is it being mined or recycled sustainably. So similarly with the balance of plant, the largest component there that makes up the emissions is the use of aluminum. And again, assumes that it's raw or first use aluminum for this analysis. So next slide. So that was looking at the beginning of life, but now we want to look at the end of life. So when the power fuel cell stack reaches end of life, we can recycle about 95% of the platinum catalyst. So here we're looking at doing how much can we refurbish our fuel cell stacks, and we're looking at a cradle to grave assessment. So we talked about cradle to gate operation, but looking at the whole thing is a cradle to grave assessment. So at Ballard, we refurbish our fuel cell stacks when they reach about their end of life, which typically for something like in a bus would be 25,000 hours or more. We use graphite bipolar plates, which are very durable. And when the stack reaches its end of life, so it's not producing enough power anymore, those plates are still able to be reused. So we can refurbish a stack, which means remove the MEAs. We send those MEAs out to be reclaimed for the platinum, and we can put new MEAs in and reuse those plates several times. So we do that, we reuse the components as much as possible, and then those new stacks are as new and shipped back to a customer. So this provides a very significant benefit for reducing our greenhouse gas emissions for fuel cells. In terms of, I don't think batteries can do something similar at this point. So, and we've been doing that for a number of years now, and we refurbish thousands of fuel cell stacks every year. Next slide. So now looking at comparing the greenhouse gas impact of fuel cell systems for production, what would actually be on a typical transit bus. So these numbers are looking at comparing a typical fuel cell powertrain, which includes a battery as well. So it's an 85 kilowatt fuel cell and 50 kilowatt hour battery for the fuel cell bus. And then we compared that with a 350 kilowatt hour battery for a battery electric bus, which are about equivalent. And it shows that there's 75% less emissions to reduce the fuel cell powertrain from cradle to gate. Okay, next slide. So at Ballard, we consider sustainability to be an integral part of all that we do. Our products power fuel cell electric vehicles with a lower lifetime environmental impact than any other technology, and deliver true zero emission mobility when fueled by green hydrogen. We have a strong commitment to the environment as our mission is to deliver fuel cell power for a sustainable planet. We're guided by the United Nations Sustainable Development Goals, and we seek to improve our performance in affordable and clean energy, industry, innovation and infrastructure, responsible consumption and production, and climate action. So we're delivering sustainable zero emission fuel cell power, reducing our operation and products carbon footprint, and we have our own internal goal to become carbon neutral in our own operations by 2030. So next slide. And I just want to say thank you, and I'd be happy to answer any questions.
Thank you so much, Shanna. Very insightful, and maybe a bit of a different perspective on Ballard fuel cells. Besides the regular knowledge that you avail to us, a part of me is also tempted to get into a passionate discussion about mining rights in the Arctic, but I guess it's not the topic of today. If we were to stick to the topic of today, starting off with a bit of a discussion on emissions from the fuel supply side. One of the first audience questions is, so where are the greenhouse gases coming from if hydrogen's produced from solar PV? In one of the cases you mentioned earlier. If you can shed some light on that, that'd be great.
Sure. They were very little. So if hydrogen is produced by solar PV, the greenhouse gas emissions are pretty minimal, but there will still be some, for example, with the transmission of the hydrogen. So hydrogen has to be transported from where it's produced to where it's used. And so that takes power to do that. So there's, right now in the analysis, it assumes that there's some greenhouse gas emissions assumed they're going to be involved with transporting that and the refueling of the vehicle. So there are a few things in operation of the to produce that hydrogen and get it into the vehicle that will produce greenhouse gas emissions.
Sure. And so while we're on the fuel supply side, and you don't necessarily have to delve too much into the details of fuel supply, considering you're on the end use side, but there is an audience question asking about the sensibility of liquid hydrogen. Would it make more sense to invest in infrastructure, midstream infrastructure for liquid hydrogen? Can you shed some light on the scale at which it would become much more suitable to do that?
Yeah, I'm not an expert on the hydrogen itself. Certainly, if you have a central depot with hydrogen, you're probably going to have liquid hydrogen sitting there, right? So, if you have a large storage, but you're using the hydrogen on a regular basis, you would use it as liquid hydrogen. If you are on your vehicle, currently everything is compressed gas, but there is research into both things like metal hydrides for solid storage of hydrogen on your vehicle, as well as for liquid hydrogen. So it is something that people are looking at, but it's still not determined if that's going to be a viable approach. But some people are looking at it, and maybe even for things like at fueling stations, maybe there'll be liquid hydrogen as well.
Sure. Thank you so much, Shanna. And for any audience members who are much more curious to discover the liquid hydrogen side, I encourage you to join the networking session at the end as well, to come and talk to some of our fuel supply participants at the conference as well. I'm sure you'll get a bit more insight. But coming back to fuel cells, and so if we were to look at fuel cells, one of the audience questions pertains to refurbishments again. How many refurbishments on the cells are expected over the life of a typical 40-foot transit bus? At 25,000 hours, the bus will likely outlive the cell a few times over. And so what's the downtime cost associated with these refurbishments? Can you shed a bit more light on that, Shanna? Sure.
So the actual refurbishment is something that, it happens back at the, in the plant. So the time for the bus in terms of downtime is very minimal. So similar to now, buses need to have basic maintenance however often they have to do it. It's something that happens regularly. If you have to replace your fuel cell stack and get it refurbished, it would be the same thing. You would take it out, you would put in a new one, you wouldn't wait for it to come back. The refurbished ones are like brand new, so they can be used in a new application. So it's in terms of downtime, it's very minimal. And currently the cost is similar to the cost of a new stack, pretty much. But again, that's factored into the life cycle cost assessment.
Okay.
So, and at 25,000 hours, that's what they are currently. Of course, we're looking at making longer lifetimes as well. That's still pretty good, but we have ones running in London that are over 35,000 hours right now. So we have very long lifetime stacks, but we're just being conservative with that 25,000 hour number.
And so speaking of life cycles again, if you can share some, thoughts and maybe case experiences on the impact of different operating environments of the fuel cell buses in different geographies on the life cycle of the fuel cells. Are there any specific cases that come to mind to make a bit of a comparative analysis, or just if you have any general thoughts on that?
Sure. Yeah, in general, fuel cell engines are not impacted by the weather. So you can operate a fuel cell from minus 40 degrees C to plus 50 degrees C. So it doesn't really have much of a life cycle impact. So the variation of temperature doesn't impact it. You get the same performance of a fuel cell in a cold winter in Edmonton or on a hot summer day in Montreal. You shouldn't really see a lifetime impact.
Sure. And we do have one more question on the fuel cells here. So, well, the fuel cell unit is rated for a continuous 75 kilowatts, right? And so when combined with a battery or supercapacitor, what peak output can be delivered for starting and acceleration? If you can shed some light on that.
Well, the output from the fuel cell is going to be 75 kilowatts. Yeah. That's the peak power required. So it'll depend on how you've hybridized it with your bus or with your battery and how you design that. So the battery and the fuel cell technology complement each other. They're all hydrogen buses today have a hybrid battery fuel cell powertrain. And the battery works to do fast discharge of the current to provide fast response to acceleration, as well as storing braking energy, which is of course very important. But the fuel cell basically works as an onboard power generator to keep the battery charged over long and demanding duty cycles. And it provides electricity and heat for things like HVAC and things, bus cooling and heating. So it's really how you design your drive system, what your peak power would be.
Yeah, sure. And ultimately, yeah, any departing thoughts, any final takeaways for our audience here on the future of fuel cells in terms of the life cycle emissions, and how do we see them playing a role in the energy transition?
For sure. Yeah, as I mentioned, we know we need to green all of our transportation. Transit is one area particularly because it also impacts the urban pollution as well. So we need it very, very urgently. And we know that we're going to need both fuel cell electric buses and battery electric buses, depending on route choice, depending on the grid choice, how green the grid is. But we need to be looking at all of it. And I've talked about life cycle emissions here, but of course you have to look at cost and the total life cycle cost, at the infrastructure cost and all of those things. And what we see is that battery electric buses and fuel cell buses both have a role to play, and they're both going to be competitive in certain areas, but there is definitely a large role that the fuel cell electric buses will need to play. And as we scale up, we see that the costs associated with the fuel cell buses will go down and be easier to implement than sometimes the battery electric buses.
Yeah, thank you so much, Shanna. Thank you so much for your time. That was a very insightful presentation. Yet again, it really helps fill those little gaps when looking at fuel cell buses and the energy transition as a whole, and when looking at some of the topics covered at the conference as well. We appreciate you joining us here today. And yeah, to wrap up the day today, I'd like to pass on the mic to Adriana and Magali Fennet to just wrap up with closing comments here. So Adriana and Magali, on to you.
Thank you very much, Salmia, and thank you, Shanna, for that great presentation and insights. And so to close off the day, I'd like to thank everyone who attended day 2 of QTRIC's 3rd annual Low Carbon Smart Mobility Technology Conference. We heard from an amazing lineup of keynotes today from Eric Moras and learning about the Société de Transport de Laval's electric expansion with a view of fully electrifying its fleet by 2040. We heard from ABB's Stephanie Medeiros, who emphasized the importance of gender and diversity within the electric mobility sector to allow for more creative solutions. We also heard from the City of Montreal's Eric Allen Caldwell, who talked about adapting current networks by collecting, analyzing, and sharing data. And of course, we heard from Ballard's Shanna Knights, who we just heard speak about the importance of sustainability of zero-emission buses in their full life cycle. We were also privileged to hear panelists on renewable natural gas for transit, on-demand transportation, QTRIC's fuel cell electric bus project lessons learned, battery electric buses, and autonomous vehicles. I would also be remiss if I did not encourage each and every one of you to fill out QTRIC and the University of Windsor's Gender Parity in Transit Survey. Anyone in the Canadian transit industry is able to complete it, and it will help us identify how we can improve our gender equity in the transit sector. That link will be shared in the chat box in just a moment. We hope that you learned and shared a lot today, and we look forward to continuing on our last day of the conference tomorrow. Before that, I'd like to thank our sponsors once again. We have our exclusive sponsor, ABB, New Flyer and Ballard, our platinum sponsors, Proterra, Zev Clean Power, and Hitachi ABB Power Grids, our gold sponsors, Enbridge, Novabus, and Thales, our silver sponsors, and Siemens, our bronze sponsor, as well as BAE Systems, which is our event supporter. And with that, I'll pass it over to Magali.
Bonjour tout le monde. Merci d'avoir participé en si grand nombre à la 2e journée de notre marathon sur la mobilité intelligente à faible émission de carbone. C'est des grosses journées bien remplies, des conférences d'honneur à ne pas manquer, des discussions parfois très techniques mais tellement inspirantes, des expositions montées par les chefs de file de l'industrie. Nous espérons que vous y avez trouvé votre compte et que vous allez vous donner les moyens pour enclencher ou poursuivre votre transition vers l'électrification. Je tiens à remercier nos précieux commanditaires comme l'a fait Adriana, mes collègues aussi, modérateurs, techniciens, rédacteurs, coordonnateurs, tous ceux qui prennent 4 ou 5 chapeaux à chaque journée, puis notre chef d'orchestre, bien sûr, qui a fait une super job, Adriana. Finalement, un gros merci à vous tous d'être fidèles au poste et de participer. Merci. On vous attend pour le 5 à 7 réseautage à 5h30. Prenez-vous un verre, puis venez jaser avec nous. Please join us for our networking session right after this at 5:30 p.m. Eastern Time. Thanks again, everyone, for attending day 2 of our conference. We're excited to see you tomorrow or at the networking session with a drink. Thank you very much. Merci.